Welcome to my talk. It's called Malicious Contracts, and it's towards the development of a fully anonymous smart contract-powered rootkit. I'll give a little... so today we'll be talking about Ethereum, what are smart contracts, what is a rootkit, the problems with traditional... the problems in attribution with traditional rootkit approaches, how using a smart contract for rootkit C2 is a much better way to do that, and provides full anonymity for an attacker. I'll be giving a little demo, and then we'll be talking a bit about countermeasures. So about us, I'm Chris. I used to be the former CISO of Dark Matter. Then I was the CISO of THEREUM, and most recently I'm working on a fintech startup, which is trying to create the Citibank of DeFi. Long story short, we're creating a THEREUM stablecoin and a merchant acceptance layer around that. I've been doing a lot of research over the years in rootkits and rootkit technology, and many, many years ago, 2010, which is the last time I spoke at a conference at DEF CON 18, I talked about an Android kernel rootkit. I was supposed to be joined by Kyprianos Vasilopoulos today. Unfortunately, his PCR expired before he could board his flight, and he won't be able to join us. But he's the chief hacking officer of Panthera Labs and a great friend for many, many years now. And he was basically the guy who helped secure multiple Olympic Games over the years that they were happening. So how many of you here, and I can't see who's virtually, but how many of you here know what Ethereum is? Maybe show of hands. Yeah? Awesome. So it's considered the world's biggest distributed computer. And when you run an Ethereum client on your computer, or Ethereum wallet or client on your computer, basically you can access this whole massive network. And it's a blockchain, and unlike prior blockchains like Bitcoin, what made Ethereum special is this functionality of smart contracts. ETH is the native cryptocurrency of the platform, and if you've been following the markets, it's gained quite some momentum and is quite valuable these days. So, a smart contract. How many of you guys know what a smart contract is? Yeah? Awesome. So smart contracts run on the Ethereum blockchain, and basically it's a program that, just like you have on your normal computer and you install programs, those programs only run on your computer. They don't run on other people's computers. They only run on your computer. In Ethereum, by deploying a smart contract, every single node or computer that's connected to the blockchain suddenly has access to the same computer or same smart contract, same program that you created. And what's the use of a smart contract? Well, kind of like the name kind of gives it away. It's a contract, but it's a contract that's codified by code. So if we were to take an example of a real estate transaction where one party wants to sell a house, one party wants to buy the house, and there's usually a real estate broker involved in that transaction. And then there's the land registry who just swaps the names on the title deed. That's the traditional way of doing a contractual exchange. Of course, there's lots of inefficiencies in that process, as we all know and are all aware of. In a smart contract, we basically put the rules of that deal in code. In that case, let's say the smart contract would own the title deed. It would currently be in the owner of the buyer, of the seller, sorry. And as soon as the buyer sends money to the smart contract would change the name on the title deed and send it to the buyer. No third parties involved. It's all done autonomously, seamlessly, and very swiftly. So smart contracts, that's just one example of like a transaction that can be done on a smart contract. But there's many other types of transactions that can be done on smart contracts. So you can create smart contracts that basically send value from one person to another. A lot of the cryptocurrency tokens that you hear about are running on smart contracts. So there's different types of smart contracts, and they're created for different types of use cases. How many of you guys are familiar with ROOTKIT? What that is? Yeah? Seems like a few hands here. Awesome. So if I'm an attacker and I hack into a box and I want to stay hidden, then what I'm going to do is I'm going to install some software on that box. Doesn't matter how I got in, but let's assume I've already got in. I'm going to install some software on that box. What that software does is it basically hides the attacker's presence on that machine. And there's various ways that attackers do that. One way is they, let's say you type a directory listing on your machine, and you see all the good files and all the bad files that are there. If there was no rootkit, you would see all the good files and all the bad files. But a rootkit can modify the system so that when you type a directory listing on your machine, you only see the good files, and it hides all the attacker's bad files. And there's different types of rootkits. There's user-land rootkits that run in the user-land. There's kernel-level rootkits that run in the kernel. Kernel is better because it can be bypassed very easily and can be detected very easily. Long story short, a rootkit is basically a malicious program that runs on a computer that hides an attacker's presence. Now, what's the traditional approach of an attacker accessing the rootkit? The machine you see over here is the target machine, the one with the virus installed, the rootkit installed. So usually, an attacker, what they do is they install the rootkit on the machine, and then that rootkit calls back home. It sends commands back to the attacker's jump box, and the attacker is able to control the target machine that they've compromised through that intermittent jump box they've done. The reason why an attacker does not want the rootkit connecting directly back to them, to their home IP address, is because of attribution. Because if somebody knew that the attacker is the compromised machine is directly connecting to the attacker, they'd be able to go to the ISP and so on and so forth and basically put the attacker in jail or get him in trouble. So what attackers do is they use an intermittent jump box to prevent a direct attribution back to them. Now, there's a drawback for an attacker in this approach, and the drawback is that the rootkit that you install on the machine, it needs to know what that jump box is. It needs to know the IP address of that jump box. It needs to know where to send that callback connection to. And our whole industry in cybersecurity, a lot of the forensics works that we do, when a company calls us and says, hey, we've been compromised, what we do is we go to the company, we find out that the server has been compromised, we take out the hard drive, we perform a forensic image, and we try to identify malicious software on the drive. Once we found the malicious software on the drive, it could be a driver, it could be a kernel module, it could be modified binary that doesn't match the distribution's MD5 or SHA sums. We then start to look at that specific binary and we try to reverse engineer it. And the whole point is we try to find that thing in the middle, the jump box. Because that's what tells us where the attacker came from. And based on where the attacker came from, we can tell maybe, which country they're coming from, what other people or companies have they attacked, so on and so forth. So, what attackers try to do to prevent that kind of like direct attribution back is they add more intermittent servers. So here there's like 2 hops between the target server, but it could be 10, it could be 20, it could be 100. But that increases the cost for an attacker. They basically have to go hack into more servers, buy more VPSs with Bitcoin or whatever they use, and buy a lot more throwaway servers in order for them to put in line between themselves and the target server to make attribution more difficult. And attackers get lazy. Because it's a high cost for them to replicate and send up all this infrastructure, they tend to reuse it. So they'll use the same infrastructure to attack you, to attack me, to attack company A, to attack company B. And a lot of attribution these days is looking at shared infrastructure used across various attacker groups. There's a case here with Microsoft. They're saying what tracking an attacker email infrastructure tells us about persistent criminal operations, for example. This is a well-defined thing in forensics and incident response, whereby you look at the shared infrastructure that attackers use across campaigns. You look at the MD5 hashes, the binaries, and so on and so forth, and see where these things have been shared and used in other attacks. So these are the drawbacks. This is how attackers currently try to solve the problem. But what if there was a better solution? And this is where we start talking about blockchain. And you'll say this is a really weird thing to do. How does blockchain help us with C2 infrastructure? Well, I'll kind of tell you how. Well, when we create a transaction on a blockchain, doesn't matter which blockchain you use, when you communicate with a blockchain or a smart contract, all your communication with that smart contract and that blockchain is completely anonymous. Nobody logs your IP address, nobody logs your username, nobody logs your browser identity, nobody logs absolutely anything. When you interact with a smart contract, there's nothing there that anybody can tell that is directly related to you, and nobody knows who created a specific smart contract, what's the real identity between person A and person B. This is what you see when you interact with a smart contract, or you send value from one person to another person over an Ethereum network or any other network. What you see is from this address to this address. These are public key wallets. These are Ethereum addresses. In this case, we're using another protocol called Matic Polygon. But that's literally all you see, and that doesn't tell you much. You can't geolocate that. We don't know where it's coming from. And you can't really tell what's happened there. Well, you can tell that value went from person A to person B, but you can't really tell who's behind it. And now, there's ways you can actually, and what I'm saying is not entirely correct. So there's ways you can find who's behind it. And that's only if the attacker is not very smart. But I'll tell you how they can be a bit smarter. And the way you can tell is by using what are called on-chain tools, like chain analysis. So because everything on a blockchain is recorded, you could basically start from the origin and work your way through the previous transactions, eventually figuring out where this guy got his original Bitcoin from or his original Ethereum from, and that's usually on exchange. And there's a lot of blockchain forensic firms sprucing up these days that make a huge business out of tracing transactions like this. And one of the key use cases is for tracking illicit money flows. For example, when there was the case with Silk Road many years ago, which was a narcotics marketplace, a lot of the flows, the illicit flows, and where these funds eventually ended up to, and who was behind Silk Road, this type of analysis was used. However, there's ways you can obfuscate your traces, and so long as you don't buy your Bitcoin from an exchange which asks you to provide your KYC documents. And one way is using mixers which confuse the transactions and shuffle them across many others. It's very akin to money laundering, something like that. Another use case is where you can use testnet coins. You can still interact with a blockchain on a different network, testnet network, and a testnet network is basically the exact same. Think about it as a UAT testing network. It's not the production network, it's the UAT testing network. So you can use like the UAT testing network with testnet coins, and there's services that give you free testnet coins in order to deploy contracts with. And because you're not getting them from any exchange, you're not getting them from any public sources, and it's only single use specifically for this purpose of creating this anonymous infrastructure, you can remain undetected. So what you see here is a little smart contract I created. Are any of you guys familiar with smart contract programming? Yeah? Cool. There's a few smart contract programming languages. There's something called Solidity, which is the normal one. There's something called Viper, which is what I've used here. Viper is Pythonic. It uses like a Python type-like syntax. It's not really Python, but it kind of looks like Python. And what this smart contract does is absolutely looks very innocent. Like if like a cybersecurity guy saw this, they'd be like, well, what does it do? It has an admin function, where it takes somebody's address and just sets it as an admin. And then it has a reporter function, and all that reporter function does is it says log fx, whatever address you give it, and whatever string you supply. So literally all it does is, if the guy is an authorized user of this smart contract, if he's an admin, then if I call the reporter function, then all it's going to do is it's going to log, if you see on the very top there, it says event sender string, it's just going to send an event on the blockchain, and an event on a blockchain is like a log. It's like a system log. It's going to send an event on the blockchain that our rootkit will be tuned to listen to and then act on and do certain instructions on. Now, this is one way. We're sending a transaction to our smart contract. The smart contract is sending an event on the blockchain. Our rootkit's going to listen to that, but we have no way of hearing back from the rootkit and knowing what the responses of that transaction are. There's ways you can do it. I won't get into it in this talk. It's a bit more complicated and very involved. But long story short, you use the same methodology, but in reverse. Your rootkit would instead call back, have some value attached to it. It would have its own public-private key. It would be set as an admin on this contract, and it itself would send the transaction back to this event with a response of whatever transaction you sent to it. And your client-side command, control, whatever you want to call it, would pick up that and get the responses back from the rootkit. So how it works is the attacker executes the smart contract. The smart contract emits this FX event, and through this FX event, it contains various strings. These various strings could be download a command, run a command. It could be now run this executable on the compromised machine. That's basically ransomware. Or it could be shut down the machine. It could be RM minus RF, delete everything on the machine. It could be literally whatever you want it to be. So that's high level the logic, and because it's a smart contract that's giving the commands to the rootkit that rootkit is listening for, there's no attribution, right? There's no IP addresses logged. If as a cybersecurity person, I find this rootkit on my box, on my server, and I look at it, all I'll see is that it's accepting commands from a blockchain. I'll be like, okay, that's great, kind of cool, but how do I find out who sent those commands? All I'll be able to see, I'll then go to the smart contract address, and I'll see which address was sending commands to that smart contract. And I'll just see it's a dummy address with no value or whatever. And because it's come from Ropsten or some other testnet coins, I can't backpedal and find out if it came from an exchange or not, because it didn't. So this creates a completely anonymous C2 infrastructure for rootkits, and reduces the complexity and the cost for an attacker to almost nothing. They don't have to set up shared infrastructure. They don't have to do any of that stuff anymore. All they have to do is connect their existing rootkits to this C2 infrastructure. So, demo time. I hope the demo gods are kind to us. and Wi-Fi being fidgety and stuff. So I'm going to try and give a live demo. If it doesn't work for whatever reason, I have a backup video that I can show you as well. So I have already deployed the smart contract. Oh, sorry guys. How can I get my screen up here? We solved it. Sorry guys. So as I was saying, this is something called Ethereum Remix. It's basically a smart contract deployment platform. I've already deployed the smart contract. It's running over here. And it's the exact same one I showed you guys. What I'm also going to do, whoops, I'll make that smaller because it's made it massive, is I'll run the ROOTKIT. Okay, yep. Let me just check something, sorry about that. What I have here, before I get into running the ROOTKIT, is the ROOTKIT itself. And what the ROOTKIT does is, long story short, it connects the contract to the events, that FX thing, and it listens for events that come from that FX on the blockchain. So it's long story short, it's monitoring that contract and the FX events that are sent to it. And then as soon as an event is detected on that FX log, then it comes to this method that's called handle event. It extracts some parameters and it checks if we sent it a hello message. If we did, it executes an operating system command called ls, which shows my files. But that operating system file could be, that operating system command can be any command we choose. It could be delete the whole box, remove all the files. It could be shut down. It could be absolutely anything you want it to be there. So cool. That's running and listening for events. What we're going to do now is we're going to invoke the reporter function with a message hello. That, if you remember, my smart contract was listening for. What's popped up over here is my Ethereum wallet. We're running on a different network called Polygon because it's faster and cheaper, but bear with me. And what we're going to do right now is we're basically sending we're basically, what you see here is contract interaction. We're interacting with this contract. We're calling this reporter method with a hello message. And what's happening in this black screen is it's listening on that contract for the hello message to come through. And what we hope to achieve is, as soon as the contract successfully executes, is you'll see on the left black thing here a directory listing of my files. Cool. Hey, it worked. Yeah. So, yeah. Now, that's basically ran everything. Got a directory listing of my files. But this could be, I don't know, whatever you want it to be. It could be, you know what, let's create a file. Let's create a file on the system. It could be, create an account. Roger, you're giving me a tough job, man, but let's do it. Delete everything. How about I make it shut down? I'll shut it down, but then I'll have to do the presentation solo. Yeah? Okay. Yeah. Up. The screen, you know, like, as soon as this executes, it's going to shut down my computer, so I won't have a presentation anymore. But then we can just take it a bit offline. Maybe what I do before I execute it is I actually talk to you a bit about countermeasures, and then I'll go back. So countermeasures, like what I've talked about today, is like some pretty scary stuff. It sounds very scary and all that stuff, but how do you prevent this from the get-go? How do you prevent this from happening, right? The usual advice applies, run a hardened network. Everything that cybersecurity people we preach about always applies. But in addition, in this use case, you need to monitor outbound connections on your network for blockchain networks. So if you have a SOC or something, or some sort of outbound monitoring, make sure that that's monitoring for blockchain transactions. Now that becomes a bit of a cat and mouse game because there's a hyperproliferation of blockchain networks out there. There's one coming up every single day. And it's further compounded by there's various SaaS-based, not RPC-based ways to interact with blockchain networks, like Infura, if you guys are familiar with that. It's like basically interact with the blockchain over HTTP. And because HTTP is like ubiquitous in a corporate network, it's very hard for you to block it. But there's ways, chain analysis, if you're lucky and they came through, went through an exchange and they're not very intelligent. But now let's go back to the cool stuff, and shut down my machine, with a rootkit. You can't see my screen. Okay. I might need your help again. Oh, okay. That kind of sucks. Because now I can't see my screen. But I'll try and do it over here. Wait. Let's do it properly. Yeah, cool. Let's do it properly. And let's go here again. What I'm doing here is just making it go faster. Paying more for the transaction, but don't worry about that. Halas. Hey! So yeah, that's it. Thank you. Do we have any questions from the audience?
Are there any open source rootkits or exploitation tools or anything that is currently using blockchain?
None to my knowledge. And I did a lot of open source investigation around this. I think this is the first documented time this has been used. And because it has a potential of massive abuse, I don't intend to make this public. So it's just showing the methodology behind something like this at present. I do expect it to be used, though. It's quite a effective way to stay hidden.